Hey guys, welcome back. So we're going to be doing thermochemistry today. That's lecture 11. This is the first of the materials for exam 3. So that's going to be a little bit different than what we've been talking about so far. I'm going to go ahead and share my screen so that you guys can see what I'm talking about. And of course, when we talk about thermochemistry, we're going to be talking about the properties of the energy of this particular system. That's what we mean by thermo. This thermochemistry and the things that come after this are all very, very related. So you'll see that there's a lot of parallels between the enthalpy, which we'll talk about today, the entropy, which is the randomness, which we'll talk about not tomorrow, but the day after, and then the free energy, which is what we're going to, our last topic for this term. The mathematics for all of these are very, very similar. They're very short lectures. There's not a lot that we need to talk about in terms of theory, but there is a lot of stuff that we need to practice with. And so what's going to happen is we're going to go through this lecture, and then I'm going to set you guys loose on doing some problems, and then I will record talking through those problems, the in-class problems for you guys. So there are solutions available on D12, but there will also be a walkthrough of those since I'm going to make my students do them in class. It's really important that you do the problem solving for this. So let's get started. And the first thing we always do is our review. So let's get back into our review. So how do we measure the rate of a reaction? Well, we talked about this. We measure the rate by looking at the change in concentration of any species over the change in time. We did talk about relative rates, okay, just as a note, where we had one over the stoichiometry. It was negative for reactants and positive for products. We do that so that they'll all be comparable, so that they'll all look the same, no matter which species we're looking at, okay? But rate is always change in concentration over change in time. What factors affect the rate of a reaction? Well, there are a number of them. We talked about a number of different things. Things that really stand out are the things that we tried to look at in one of the labs, which is temperature, surface area, and concentration, okay? Other things that can affect that rate is other ways to change that concentration. We can increase the pressure of a gas. So we can look at changing concentration. We can look at changing temperature, and we can look at changing surface area. Okay, so those are things that we consider when we look at what can affect the rate of that reaction. So there are some other things that we can talk about, like adding a catalyst, stuff like that, but those are the big things that stand out in my head. And if they stand out in my head, you might want to know about them. What's required to get a product during a reaction? Well, there are 3 specific things that we've talked about. So in order to get to a product, my reaction molecules need to collide. So that's an issue. I need to make sure that there's a collision. That collision has to have sufficient energy. So the energy of that has to be greater than the energy required to get over that hump for the transition state. So the energy has to be greater than EA. The other thing that we've talked about is it has to hit with the correct orientation. Now, what specifically that means is not important to you. Just know that orientation is a part of this. Okay, so if they don't hit in the right way, they're not going to be able to react to give you what you need. All right. Activation energy. We have to define an activation energy. Well, I'm going to draw on this graph right here. So my activation energy is going to be the difference between my starting material and that transition state. So this they call it a double dagger. I don't know why they call it that, but that's what they call it. It's a double dagger. And that difference between those 2 phases is the activation energy for that species. Okay, when we look at activation energy, it's always from where I start to the height of that peak. Okay, my transition state exists here. My transition state, for a definition, is not something that I can isolate. So it's not a permanent species. It is a midway between reactants and products. It is not something that I can isolate and measure. Now, there are ways that we can do that if we go through a lot of rigmarole to make it happen, but that is not something that we typically see and are able to pull out and isolate. An intermediate, on the other hand, is what exists in the well between 2 steps. Okay, so an intermediate is something that we can look at, measure, pull out, say, oh, okay, all right. And it's made in one step and consumed in the next. So an intermediate is made and consumed. Okay, so there's my intermediate. Relative reaction rate. That's what we were talking about right here. We do the correction on my reaction rate. So 1 over A, concentration of A, concentration of time, changing concentration versus time. And this is for a reaction that looks like AA going to B. And that'll be equal to 1 over B times the change in B over time. And so we've taken into account whatever the stoichiometry is, as well as whether it's negative or positive, depending on which side of the reaction it's on. So that's a relative reaction rate. An instantaneous rate is if we were to look at a rate curve like this. We could take any particular point and demarcate that point and draw the tangent to the curve at that point. I'm really bad at drawing tangents, but it's a tangent to the curve, and it's the slope of the tangent at that point. Okay, so that's the instantaneous rate. An average rate can be measured at any time. So any time difference is an average rate. So this really talks about an average rate rather than a particular point in time. An initial rate is at time equals 0. So it's an instantaneous rate where time equals 0. Okay. When we talk about the heat of a reaction, and I'll do that here, we're looking at the difference between the reactants and the products. And that's the heat. Okay. So there you go. Now, these two diagrams are here so that we can talk about some things that exist in them. So again, we have our activation energy for this reaction is there, but we have one for this one also, which is here. And of course, that red line is an uncatalyzed reaction. The blue line is a catalyzed reaction because we start and end in the same place, the same energy for my reactants and my products. So reactants here, products here, but we have a different pathway between the two. So I know that this is a catalyzed versus non-catalyzed, and catalyzed is always going to be the lower one. Catalyzation works because we've lowered that energy. So this is catalyzed. One of the other things that we can see in this particular diagram is that it is very clearly a different process because there are two steps involved in that catalyzed reaction, whereas it looks like there's only one step in the uncatalyzed reaction. Okay, so understand that the fact that there are two peaks there means that there's an intermediate that exists in the middle and that there are two steps involved in that process. Okay. When we look at the energy diagram over here, we can look at the difference. So we can calculate a heat for that reaction as well. That's the same thing that we talked about over here. We can calculate an EA for both steps. This is step 1. This is step 2. So there are 2 steps involved. We do have an intermediate. Each one has its own EA, but there's one heat of reaction between the reactant and the products. Okay, so those are some of the things we can talk about with those graphs. I don't think there's anything else I really ask you about. I mean, there's nothing that stands out to me. You might get asked what's the actual energy for this EA. So what is the value on that line, the energy line? So if it's labeled, what is that number? And you might get asked what is the actual value of the heat of reaction, so the difference between this point and this point, but you need actual numbers on that graph to be able to do that. Okay. In a reaction, I double the concentration of the reactant and the rate goes up by a factor of 4. What is the order of the reaction? Well, I have doubled the concentration, rate goes up by 4, then I'm looking at 2 to some exponent. 2 to some exponent equals 4. That exponent is then 2. Okay, so that's squared. If the rate doubles, so we go 2 to some exponent equals, equals 2, then y equals 1, because it's the same change for both of them. And if you've doubled that concentration, so that ratio is equal to 2 there, but this does not change. So there's absolutely no change here. Then that Z equals 0. Okay, because no change is a 0, right? So that's what we're talking about in terms of orders from that kind of discussion, okay? All right, what else can we look at? Really? No, really? Oh, here we go. For the reaction F2 plus 2ClO2 goes to 2FClO2 with the following data, what is the order of each reactant in the rate law? Okay, so how am I going to find this? Well, I need to look at what data I have. So in my first column, that F2, I have the same concentration for the first 2 rows and different concentrations for the ClO2. So I can use those 2 rows to find out what the order is with respect to ClO2 because the F2 hasn't changed. For the last row, I see that I double the F2, but my concentration is still 0.01. So I can use this row and this row to do F2. And I can use this row and this row to do the ClO2. Okay? Because we have to maintain one of those concentrations as the same and vary the other one. Because we only want to consider one concentration at a time. So we want to see what that looks like. So I always do bigger number over smaller number. That way I get, integers or, something greater than 1 or greater than 0 that I can deal with. So if I'm going to look at ClO2, I have 4.80 times 10 to the minus 3 over 1.20 times 10 to the minus 3. And that's equal to 0.04 over 0.01. And we're looking for the exponent on this right here. That's what I'm solving. So I do my ratios, 4.8 times 10 to the minus 3, divided by 1.2 times 10 to the minus 3. And that gives me 4, and that's equal to 4. So my x is 1, because we have the same change in both of them. Okay, awesome. So that means my ClO2 is 1, and I go ahead and write that there just so I can keep track of it. That's how I handle it. When we look at our F2, we see that that second row is 0.2 over 0.1, and I'm writing them in the other order this time. This is going to be a different exponent. It may be the same, may not be the same, so we use a different letter for it. And then the concentrations that I have in both of these cases, or rates that I have, 2.4 times 10 to the minus 3 goes with the 0.2, and 1.2 times 10 to the minus 3 goes with the 0.1. So 2.4 times 10 to the minus 3 divided by 1.2 times 10 to the minus 3, because I can't do that kind of math in my head. That's 2, this is 2 to the y, and so y equals 1. So that is first order as well. Go, awesome, that was so exciting. So that means that my rate law is going to have the form rate is equal to k times F2 to the first times ClO2 to the first. Okay, so my rate law always equals k, which is the rate constant, times each concentration to their exponent. Okay, if that exponent is 0, it doesn't appear. Okay, so that's that. Now, I can also take this data to solve for k. Now that I know what my orders are, I can take one of these rows and I can say, all right, the rate, and I'm just going to write this down here. So rate equals k times F2 to the first times ClO2 to the first. That's a 1, I swear. My rate for this first row is 1.20 times 10 to the minus 3. And I got that from the table. It says initial rate right there. And that's equal to k times my concentration of F2, which is 0.1 to the first power, times ClO2, and actually, hold on, sorry. That's 0.1 to the first times 0.2 0.01 to the first. And so if I solve for k is equal to 1.20 times 10 to the minus 3 over 0.1 times 0.01. And I can do that happy math, 1.20 times 10 to the minus 3 divided by 0.1 divided by 0.01, and it gives me 1.2. Okay. Now, I know that this rate is in molar per second, all right? So I can find the units for K if I really wanted to. I am not concerned that you know what those units are. All I care about is that you can find the value and that you know where to put it. So rate equals 1.2 times F2 to the first times ClO2 to the first. Okay. So that's the reaction, the rate law for this particular set of data. Now, I didn't specifically ask you to find K with this set, but that is how I do it. Okay. So if you were asked to do so, that's what you would do. And that's a fairly common set of questions is, all right, here's your data, find the order for each one. What's the value of the rate constant? What does your rate law look like? Because I want to know that once you found all those numbers, you know what to do with them. Okay? So there's that. If you have questions, comments, problems, let me know. So what does this say? I have a reaction as first order with a reaction of C4H8 goes to 2C2H4. If this is a first order reaction, what equations apply to determine the half-life of C4H8? So I know that C4H8, this reaction here, is first order. And on my happy exam handouts, there is a table that exists on page 6. And there are sets of equations in that. Now, they're not labeled as to which is which, but I know that one of them applies to zero order, one of them applies to first order, and one of them applies to second order. And it's your job to remember which one is which. I know that first order hold on just a second. First order is the natural log of the concentration. Second order is 1 over that concentration. And zero order is just concentration. Those are the linear plots that go with those. And so those are the ones that I'm going to be looking for. Okay, so I want to look for the set of equations that has the natural log. I can find that in here. And in that box, it says that T1 half, the half-life, equals 0.693 over K. Okay, so that's the equation that applies to find the half-life. What would be the integrated rate law for this reaction? Well, the integrated rate law is going to look like, for first order, it's going to be that natural log of A T equals minus K T plus ln of A0. Now, if I was being really strictly correct, I would replace that AT with the C4H8, but I didn't do that this time, but that's technically more correct, okay? Which graph would be linear for this reaction? And again, linear for this one is going to be the natural log of concentration versus time. Okay, so that's the one that'll be linear. How can you use the data to determine the rate constant? Well, once I have the data, I can plug that into my rate law, right? And I know that my rate is equal to K times C4H8. Okay. Now, this is my integrated rate law right here. This is just my rate law equation. So if I know what the concentration of C4H8 is, I plug that in and I can solve. If I know a rate and I know what that concentration is, I can solve for K, just like we did in the last one. Another thing is that the slope of this line, and I can't remember if it's positive or negative, but the slope of the line is equal to K. And if the slope goes like this down, which I think it does, and it's the negative of that, If the slope is negative, then you take the negative of it to get k. So there's that. One other thing. Oh, where do we go? The rate constant for the first order decomposition of cycle butane C4H8 at 500 degrees is 9.2 times 10 to the minus 3 seconds. How long will it take for 80% of a sample of C4H8 to decompose? Now, I can use my integrated rate law to do this. There is another form of that equation, which is not given in the exam handouts, but I can give it to you here. And I make this available. So, okay, good. The problem that I have with this particular set of equations is that most people don't know how to go from plugging in for this. So my concentration for AT at a given time is 80%. So 80% of it is gone. That means I have 20 left is equal to negative K times T. And my K I have, they gave it to me, negative 9.2 times 10 to the minus third seconds minus 1 times T, which is what I'm solving for, plus the natural log of 100. And most people don't know how to go from here to solving this equation for T. So that's why I like to give the other format of this equation, because it's the natural log of concentration of A at time T over concentration of A at time 0 is equal to negative KT. And so this one you should be able to use without much of an issue. So what we find is that it's difficult for people to move between these two in terms of solving it. So if my AT, again, what I've said is that at my time 0, it was 100%. I know that I want to know how long it takes for 80% of it to decompose, so that means I have 20% left. And so that's what I'm plugging in here. As the natural log of 20 over 100 is equal to negative K, which is 9.2 times 10 to the minus 3 seconds to the minus 1 times T. So I can take the natural log of 20 over 100, and then I can divide that by negative 9.2 times 10 to the minus 3, and that gives me T is equal to 169.41. Okay, and it really should only be 2 sig figs, so I would do that as mode scientific 1, which is 1.7 times 10 to the 2. And that's in seconds. And I know that because this is seconds to the minus 1. So that's in seconds. Okay? So that's how I would do that. Questions about that? Now, without this equation, I wouldn't necessarily know how to solve it. I mean, I know that the math works that way, but not everybody does. And so sometimes what we see is that we get people taking the natural log of 20 and it's the natural log of 100, and that's not how to combine those two things. Okay, so there's that. Questions about that? All right, I will do my best if something like this exists on the test to include that equation for you. Okay, so that's my review. Questions, comments, problems, concerns, any of that stuff. I hope not, but if you have them, please let me know. Reach out. I will do my best to answer those questions. Thanks, guys. I will see you soon.